This $1 microcontroller is the world's smallest Minecraft server, with infinite world generation, multiple biomes and caves, crafting, mining, building, and pretty much everything you'd expect in a survival Minecraft server, all running on a chip tens of thousands of times weaker than a modern smartphone. Now, hold on. Minecraft servers are notorious for acquiring gigabytes of
wham.
But here, I'm claiming to do it in under 300 kilobytes. And while computer processors from 2 decades ago measured their clock speeds in gigahertz, this thing tops out at 160 megahertz. How is this possible? Now, obviously, this isn't running an authentic Mojang-approved Minecraft server. To make this work, I wrote my own Minecraft server from the ground up in the C programming language, making sure to squeeze every bit of performance out of the target hardware. That's why I'm calling the project Bare Iron. It requires working very close to the bare metal hardware that it runs on. First, let's set the record straight. I'm not saying that the Nachian server is horribly optimized, even though it is, and that somehow just writing better code leads to a 1,000,000% performance increase. Instead, I'm just cutting corners wherever possible, prioritizing performance over features in every step of the way. And one major example of this is terrain generation. At its core, a world generation algorithm is just a bunch of random noise, adjusted to look like a recognizable landscape. Of course, it can't be purely random because then the terrain wouldn't make any sense. Instead, vanilla Minecraft uses Perlin noise, which is an algorithm that generates a continuous noise gradient, creating a sort of foggy or cloudy texture instead of pure TV static. But now this is the problem of being too smooth. So to fix that, multiple layers of Perlin noise are stacked in so-called octaves to create more natural looking randomness. To determine specific landscape features, such as hills, rivers, and vegetation, various biome-specific parameters are applied to the noise maps. In the overworld, these are temperature, humidity, continentalness, erosion, weirdness, and depth. This is still just the tip of the iceberg when it comes to world generation in vanilla Minecraft. It should be no surprise that simply loading the world for a party of friends requires a beefy computer. While Perlin noise isn't computationally expensive, it's not free either, especially when you have to stack multiple octaves. The field of biome parameters also adds complexity and memory usage, which is something we really can't afford. This is a big part of the reason why a Minecraft server requires a ton of RAM. Chunks that are actively in use are stored in memory to avoid repeating these expensive calculations. But on my microcontroller, doing so for just a handful of chunks would already take up more RAM than I have, and I want this thing to support infinite world generation. In essence, I need an approach that allows for a continuous noise gradient without layering expensive noise maps, supports biome-specific features without complicated parameters, and doesn't require storing anything in the server's memory. Effectively, what I'm asking for is a magic function that can tell me what block sits at a given coordinate without referring to memory or calculating expensive noise maps. And I think I know exactly the right tool for the job. When it comes to cheap gradients, nothing beats the efficiency of bilinear interpolation. While it might sound like a bunch of word soup at first glance, you've probably actually encountered bilinear interpolation yourself. For example, when resizing a pixelated image to an arbitrary factor, the borders between the pixels often become blurred. This is because image software often applies bilinear scaling, and crucially, the result of this is a continuous gradient. That already ticks the first item off the list, but how do we obtain the underlying noise without having to store or generate a noise map? I mean, in the image example, the pixelated icon could be considered the noise map. And yes, when we scale up a bunch of actual noise, we do end up with a smoother noise gradient, comparable in some ways to the Perlin noise of vanilla Minecraft. But this requires having the random data to begin with. If I just threw a random number generator at it, then the terrain would change every time it's loaded. I need to anchor the RNG to something deterministic. For example, the X and Z coordinates of the chunk. For any given chunk, these will obviously never change, but they're also kind of predictable. This is what it would look like if I used just the coordinates for the noise data. Since the coordinates change incrementally, the terrain follows a similar pattern. But what if, instead of using the coordinates by themselves, I'd provide them to the RNG function as a seed? That way, I'm still getting a random looking number, but it'll be the same random number each time. This now ticks the second item off the list, because all I need to do to get a data point for the noise is generate one pseudo-random number, which is a relatively cheap operation, even on a very slow processor. Let's see how this works in practice. Say I'm trying to generate the surface of just one chunk for now. There are 4 corners for this chunk, each with unique coordinates. I pass these coordinates into the RNG function to get fixed-digit pseudo-random numbers. The last digit of these numbers is then treated as the height of each point. And finally, to generate the shape of the terrain, I apply bilinear interpolation on these 4 points. Any adjacent chunks will share up to 2 points with this chunk, making the interpolation continuous across chunk boundaries. Continuing this pattern, we get something resembling irregular terrain. For this example, I'm using just one of the digits from the random number. Adding up multiple digits makes the terrain more regular. Kind of like how the more coin flips you do, the closer the distribution gets to an even 50-50. In turn, reducing the amount of factors makes the terrain more jagged. Using just these parameters, we can play around with the shape of the terrain. Of course, I'm not actually using digits from a decimal number. Under the hood, it's a binary value, and I'm just picking how many bits to use for each factor. Now, that's all well and good for surface terrain, but what about the underground? In vanilla Minecraft, caves have their own separate algorithm, and in newer versions, even their own set of biomes. That sounds like we're about to double the workload. Then again, we've already generated valid terrain, so why don't we just repurpose that? My approach was to simply mirror the existing surface terrain. In-game, this ends up looking a lot like one of those wide deep slate caves, and as long as you don't think about it too much, it passes as good enough. All that was left was to sprinkle in some ores. Once again, due to cutting corners, these don't come in veins like they do in vanilla. And to make sure that mining isn't an entirely extinct activity, I hid the diamonds under the lowest point of most of the cave volume. Let's take a look at our list again. The next 2 points mention those biome-specific features, but in this case, I don't really see a reason to calculate temperature or humidity, given that our noise is, at the end of the day, relatively primitive. Instead, I'll just sprinkle trees throughout the forests, cacti and dead bushes throughout deserts, short grass shrubs among the snow, and so on. The position of these elements is determined by one of the random numbers of the chunk corners, so that's not really that interesting. The biomes themselves, though, well, that's a different story. What would make the most sense is to layer some kind of biome noise on top of our terrain noise. However, the linear interpolation trick starts to fall apart on a scale like this. And remember, I'm trying to avoid unnecessarily layering noise, as that would double the compute requirements. There's also a lot of work required to make sensible transitions between biomes, and to prevent anomalies like overly tiny or huge biomes. So I decided to go with a simpler tile map approach. Basically, we'll make each biome a circular island surrounded by other such islands in a grid. The type of biome that each island holds is then determined by a small, repeating pattern table, which is calculated from the world seed. Yes, this does make each biome the same size and makes the placement of biomes painfully grid-like and predictable, but as you'll soon find out, this is a necessary sacrifice for performance. To make the landscape unique for each biome, we just have to adjust the amount and scale of the random factors that we combine. In the forest or plains, 4 separate factors are used to get mostly flat terrain with occasional features. In the desert, terrain height variation is limited to 6 blocks and never goes below sea level. In snowy plains, terrain height varies by up to 14 blocks, using only 2 random factors to increase the variety of hills. Checking our list now, there's only one thing left. We must avoid storing any of these blocks in memory. For world generation, this just means regenerating the chunks each time a player loads them. Of course, that is a lot of repetitive compute work, but the silver lining is that we only need to do this when the player crosses into a new area. Otherwise, the Minecraft client is able to keep nearby chunks in its own memory. However, in many cases, we still need to be able to query specific blocks, like to know what item to give a player when they've mined something. It would suck to have to regenerate the entire chunk each time that a player mines a block, but luckily, we don't have to. Chunk corner coordinates can be obtained from the player's coordinates, and by linear interpolation can return the height value at any point on the plane. So by design, this approach already lets us query for specific blocks with minimal compute and no net memory usage. That said, I've left one last thing unanswered, and that's about what happens to the blocks that get mined or placed. While we're not storing terrain data, we do have to store player-made block changes. For this, I'm using an array of 6-byte data structures. 2 bytes for the x-coordinate, 1 byte for the y-coordinate, 2 bytes for the z-coordinate, and 1 byte for the block ID. When a player changes a block, the new block at that location is stored in the first available array slot. And when that change is undone, as in the terrain is returned to its original form, the entry gets cleared, ensuring tight packing of only necessary data. Unfortunately, these data types set a build limit for 32,000 blocks horizontally and 256 blocks vertically. Using these smaller data types just takes up less memory, so that's where the compromise comes from. On my microcontroller, with this layout, I have enough memory for about 25,000 block changes, which is equivalent to digging out just 1.5 chunks. If I used larger data types, that would cut in half the amount of changes you can make. This also means that there are only 256 different block types, but considering that I don't plan on implementing wax slightly weathered cut copper stairs anytime soon, I think this'll suffice. Let's take a step back and see how all of this performs. On my desktop computer with a Ryzen 5 3600 CPU clocked at 3.6 GHz, each chunk takes about half a millisecond to generate. On the ESP32C3 microcontroller, which you can easily pick up on AliExpress for less than $1, it takes, on average, about 200 milliseconds, that's a fifth of a second, to load one chunk, which in most cases is perfectly playable. Of course, this performance is only possible thanks to the minimalistic algorithm we just discussed, but in order to implement it efficiently, you need a very good low-level understanding of the programming language you're working with. And if that's what's keeping you from taking on a cool project, then let me introduce you to Kodi.tech. They're the sponsor of this video, but it's also a genuinely great way to learn a programming language. When I first started learning how to code, I would scour the web for JavaScript tutorials that would keep my attention, but everything just seemed so dull. I didn't have Kodi back then, but that's pretty much exactly what I was looking for. Think of it as Duolingo, but for programming. Lessons are interactive and split up into digestible chunks. Each new subject has a clearly defined and easily achievable goal, with practical challenges that get you writing actual code. It's the kind of thing that you can pick up and put down for 5 minutes every day just to keep up your streak and end up actually learning how to code without even noticing. And it's not just for beginners either. I'm actually using Kodi myself to learn Rust, which arguably might have been a better choice for this project, but I digress. If Kodi sounds right for you, use the link in the description to let them know I sent you. Minecraft isn't much fun without the mining and crafting, so here's how I implemented those aspects. You might have already noticed that whenever I mine a block, the item for it goes straight into my inventory. In other words, blocks don't drop anything. Simulating those item entities would take up valuable memory and compute resources. I did end up implementing the animation of an item flying towards you, but that's purely visual and doesn't account for distance in any way. On the topic of items, crafting is implemented in a rather crude manner. For a modular system, it would make sense to define 3x3 matrices for each crafting recipe and then use a kernel-fitting algorithm to match those onto the crafting grid. Again, that's the modular solution. But those matrices take up a sizable amount of memory, and that kernel-fitting algorithm is relatively complex. Instead, I opted to make my code look 10 times more disgusting and unmaintainable just to save a bit of performance. In a nutshell, the function first counts the amount of slots taken up by the recipe, making note of the first item it encountered and tracking whether the rest of the items are identical to the first. Right away, this lets us implement some simpler recipes really cheaply. To craft a furnace, you just need to check that there are 8 items in the grid, that the first one is cobblestone and the rest of them are identical, and that the central slot is empty. After just these 4 operations, you have confidently eliminated every other recipe. Or swap out just one of those conditions and you've got the recipe for a chest. For recipes with more complex shapes, you simply use the index of the first encountered item and check for the other items in relation to it. For example, when crafting shears, there will be 2 items total. The first is an iron ingot, and the second is also an iron ingot, either on the bottom left or bottom right of the first ingot. These conditions will then be satisfied regardless of where the recipe starts in the crafting grid. This also lets us reuse similar recipes. For example, instead of having 5 recipes for all the pickaxes, we can define one shared shape and switch the output item based on the material in those first 3 slots. That's the crafting table, but what about other containers? The furnace might seem much simpler in comparison, given that it's only got 2 inputs and an output. But in vanilla Minecraft, furnaces are among the few containers that take time to process their inputs. And, unlike a crafting table, you can leave your items in the furnace and come back to it later. This requires not only storing item data for each furnace, but also assigning some kind of timer to that furnace and keeping it updated. That's yet again more memory and compute. Ultimately, I felt like replicating the exact mechanics here wasn't worth it. Instead, I made the furnace function just like the crafting table. In goes a recipe and out comes the product. No waiting, no item storage. Initially, I was gonna leave it at that. After all, the crafting table and furnace are what define a Minecraft base. What more could you need? But after playtesting this with a few of my viewers, the demand for a chest turned out to be loud. Without a way to share items, some people ended up starving despite others having tons of food. When mining, we'd often fill up our inventories to the point where they started overflowing into the armor slots. So yes, I added the chest. But this now meant that I was faced with the annoying task of finding where to store the item data. If you're not familiar with embedded programming, or just programming in C, it might not be immediately obvious why this is a problem. Long story short, I can't just allocate memory whenever it's needed. I need to know ahead of time how much of it I will need and where. Otherwise, I risk running into issues like heap fragmentation, which will eventually crash the program if you're not careful. Since block changes are stored in one big array, it seemed like the obvious answer was to store the item data in the same array next to the chest, as effectively invisible blocks. This actually works out better than you'd expect. Here's the data structure for a block change again: 16 bits X, 8 bits Y, 16 bits Z, and 8 bits block ID. And, as it just so happens, the way I store items is by using a 16-bit ID number and an 8-bit number to encode the stack size. By pure coincidence, it works out that each block entry can perfectly store 2 item entries. This is one of the excuses for why I don't use a hash map for the block changes. Not only does it save on memory, but it allows me to do silly hacks like this one. And finally, to add some more dynamics to the game, I implemented health, mobs, and combat. Let's start with health and hunger. Fall damage was by far the simplest type of damage to implement. You just keep track of the Y level at which the player last left the ground and subtract it from the Y coordinate once they touch the ground again. Healing, on the other hand, wouldn't be so straightforward. The hunger mechanics in modern Minecraft aren't that simple. You have to keep track of health, hunger, saturation, and update all those variables over time based on what the player is doing. For a moment, I considered taking inspiration from the old alpha days, where simply right-clicking with food in your hand would directly replenish your health. But luckily, I found a workaround that let me implement the hunger system completely for free. When you're moving, your game client sends movement packets to the server at a rate of about 20 per second. And crucially, when you're not moving, you send just 1. Since my server has to process these packets one way or another, it's effectively a free indicator of how much the player is moving. I added a counter that decrements each time one of those packets is received. When it hits 0, your hunger bar is reduced by 1 and the counter resets. Increasing saturation is then just a matter of adding to this counter. Of course, for any of this to actually matter, I had to add mobs. Hostiles to act as a threat, and passives to act as a food source. Passive mobs simply wander around aimlessly in one of 8 directions. To save memory and compute, I made the decision to store only integer positions, which is why it looks so choppy. And hostile mobs have an equally simple algorithm. They just move in the direction of the nearest player. No pathfinding, no obstacle avoidance, just walking straight towards the target. The one major difference is that once a zombie gets within 2 blocks of you, it starts dealing 3 hearts of damage per second. Now, you'll notice that's way more than vanilla, but that's to compensate for the otherwise dumb and predictable movement. This damage can of course be decreased by wearing armor. To reduce complexity, I'm using the old damage reduction formula before the combat update. This means that a full set of diamond armor absorbs nearly all of the impact, but I think that's fair given that on a microcontroller things can get pretty laggy, even after all these optimizations. These are sort of the main 3 challenges that I kept refining throughout development, but of course there are several more places where corners have been cut, and several implementation details that would require separate videos to properly discuss. For example, there are no random ticks. Saplings won't grow on their own, so you have to use bone meal from composters. Mobs won't appear randomly either. Instead, there's a chance for one to spawn each time you cross a chunk boundary. Liquids flow instantly to avoid having to queue block updates in memory. Torches are sent after all other blocks, forcing the client to calculate light data without having to do it on the server. I could go on, but I think you get the point. This was a much bigger project than I can describe in one video. Naturally, now that everything was implemented, the final step was to test this out with real players on a real microcontroller. And, to my surprise, it wasn't a total failure. I mean, sure, with more than 3 players online, things do start to lag quite a bit, but I'd say it's comparable to playing 2v2t during peak hours. Now, there are a few things to consider when playing with real people. First of all, the server trusts the client fully. If your client tells the server that it's now got a stack of diamonds in its inventory, the server won't even bother to check, because that would require additional computation and memory. Similarly, if your client said that it just mined an entire chunk of blocks in less than a second, the server would happily accept that as fact. What I'm saying is that this really isn't a good idea if you can't trust the people that you play with. Secondly, there's no network compression whatsoever. In a vanilla server, when an outgoing packet exceeds a certain size threshold, its contents are compressed using the zlib compression algorithm. Needless to say, compression is very computationally expensive, so it's out of the question. This makes it near impossible to host a server on a slow internet connection, and makes the game unplayable to players with bad internet. This also means that, although on modern computers the server can easily generate hundreds of chunks per second, sending those chunks quickly becomes unrealistic. With all that said, you might be wondering, what's the point of all this? Why did I spend a month of my life developing an embedded Minecraft server? Well, honestly, I just really like the idea that this tiny little chip that costs $1 frickin' dollar and consumes half a watt can run something as advanced as Minecraft. As a great man once said, science isn't about why, it's about why not. If you want to try this for yourself, either on a computer or an actual microcontroller, I'll leave a link to the GitHub repository in the description. There's no payment or anything, though I would appreciate if you subscribed. A big thanks to my channel members for their patience, and thank you for watching.